Typically, glue constraints are enough to create an awesome destruction sim, but if you'd like, you can experiment with adding in some soft constraints as well for some interesting bending or deforming effects. Now to create this soft constraint demo, I'll just copy our current sim setup, and I'll rename that and dive inside. And anytime that you're making copies of entire sections like this, always make sure to change your cache locations so that you don't accidentally overwrite another simulation. So in this case, instead of just calling this RBD sim, I'll call this RBD soft constraints. And then to add a soft constraint to your sim, you can go inside the DOPNet and to the constraint network. And we've actually already set this up when we were talking about how to merge together different constraint types into one simulation. And although we've added this soft constraint definition, it's not really doing anything because none of the constraint names on our constraint geometry have had a name of soft to match this soft constraint relationship here. Under these soft constraint parameters, the main one that we'll be interested in is the stiffness parameter. We can probably just leave the rest length at the default and the damping ratio as well, although you can experiment with that one if you would like. And then to actually use some of these soft constraints, we can jump out of our DOPNet and go to our constraint geometry here. And in this case, I want to make sure that all of our clusters and clumps are still considered glue with infinite strength of -1, but we can define all of the other areas as soft constraints, but only once they're broken. If we define them all as soft constraints right away, then all of the sections of the building could just sag down, and that would look pretty weird if everything just sags immediately. So we want them to turn into soft constraints only when the initial glue is broken. Now for this simulation, we can probably just set up the constraint switching on our default constraint properties stop here, and you can turn on this switch constraint type when broken option. And this will default to turning those constraints into a soft constraint, and by default this constraint name of soft will match the name in DOPS. You can see that's the same as the data name here. And I mentioned that we want to make sure that our glue islands, those clustered together areas, never turn into soft constraints, but since we've defined a strength on those of -1, those should never break, so they should never turn into soft constraints either. So in this particular case, I'm not really worried if it looks like the soft constraint is enabled for that type, since it'll just never really happen. To take a closer look at how this is working internally, we can pull up the spreadsheet for our constraints and look at those primitive attributes. And you can see this is using a next constraint name of soft for all of the constraints. And once that glue is broken through a collision, it'll turn into this constraint type. Now to art direct this sim, you'll want to play around with these stiffness settings, and you'll probably have to run a lot of versions to find something that looks good, but without getting into dialing in the exact stiffness setting that we want, we can first go into the DOPNet to see if this constraint switching is working correctly. And we'll make sure that our RBD packed object for the building has its display geometry option set to off so that we can see our constraints a bit more clearly. And then if you start stepping through the simulation, you should see the constraints change color once they're broken from collision with that creature. And you can see that as the monster's pushing into the building and breaking those constraints, that those are turning white, which matches the guide color for this soft constraint relationship here. You can see that under this guide options tab. So it looks like our constraint switching is working correctly. Now if we run a flipbook for that sim with the constraint switching, we get some slightly strange results, but they're pretty interesting actually. And right now we're getting no constraint breaking in our soft constraints, so they always kind of stay stuck to the building no matter what. Now, glue constraints will break from collision impacts, but other constraint types like soft constraints will not be broken from collision like that. They will always be trying to maintain their rest length between the pieces. So in order to implement some constraint breaking in these soft constraints, we'll have to do a little bit of extra work in our DOPNet. Before we start implementing the soft constraint breaking, let's also check inside our DOPNet to make sure that our infinite strength glue island clusters are being maintained. And if you look at your constraints, you can see that it looks like we do have these little glue clusters embedded within all of these soft constraints here. So it looks like all those clumped together sections are being rigidly preserved, which we want. Now, in order to add the constraint breaking, we need to add a solver to the third input of our constraint network. And this will be a SOP solver. Now, if you connect that SOP solver to the third input of that constraint network and then dive inside, you can see that it automatically sets up a few different imports from our DOPNet. This DOP geometry is our main RBD sim data, and it also offers us impact data and feedbacks and the relationship geometry. In this case, we're just concerned with the relationship geometry, which will be all of the constraints that we've defined in our simulation. And because we're running this for our constraint network, we want to make sure that this is what we output. We don't want to output any of those other things. So I'll drop in that output and connect the relationship geometry to it. Now, I've jumped a few frames ahead in the simulation, but you'll see that the constraints themselves in the SOP solver are not moving at all. This is a bit more obvious if we jump up to DOPS and take a closer look at the area his arm is colliding with. And you can see these constraints are all moving and updating to reflect the correct positions of the sim pieces. But in the solver, they're always shown at this start frame rest state. And we want to make sure that we always want to output these constraints in the same state. It can really mess things up if you start to change the position of these. Bullet will internally keep track of all of these updated positions, and you can modify the data on this constraint geometry, but don't start moving things around in here. You can temporarily move this constraint geometry around as long as you don't output it. For example, we might want to use this DOP geometry to update the constraints to their correct positions. This DOP geometry seems to often not bring in the actual RBDs unless I point this at a specific RBD object. So in this DOP geometry object mask, I'll just type in RBD packed object underscore BLDG, and you'll see that this is now bringing in all of our RBD geometry. Now we can use this imported geometry to update these constraint positions for the purposes of doing checks against their new position, if that's something that you want to do. So to update those positions, you can create a point wrangle, and I'll call this set current position, and we'll connect our relationship geometry to the first input, and in the second input, we'll put this DOP geometry. And then I'll use a bit of vex that will find the point containing a matching name in our DOP geometry, and then it'll get the point position for that matching name, and it'll set the constraint point accordingly. So if we toggle that wrangle on and off, you can see it moving those constraints to match the moving positions in the sim. Now the most common case where I'll do this sort of thing is to check if the position is below a certain Y value, in which case I will perhaps set a very low constraint strength so that these pieces can easily break up on impact with the ground. For this shot, I'm not really bothering with that because we don't really see the ground impact, and even in cases where you see it well, it might not matter too much if that's going to be filled with tons of dust, but that is a very common, helpful technique. Now, if you update the positions like this, you would have to do your check and then transfer that data back to your relationship geometry. That could be a group or an attribute defining which constraints that you want to weaken or break entirely. So in this case, perhaps we could check if the position y is less than a value of 10. And if so, we'll set an integer attribute called weak and set that to a value of 1. And anytime we're setting new properties or groups on our constraint geometry, we generally want that to be on the constraint primitive lines, not their individual points. So I'm going to promote this weak attribute from points to prims. And we'll set that promotion method to maximum so that if any point is below a y value of 10, that entire primitive line will be tagged as weak. And then we can copy that weak attribute to our constraint geometry. In this attribute copy, we'll just select weak for the name, and we can leave everything else as defaults. And if you want to test that to make sure it's being set and transferred properly, we can drop in a blast. I'll call this check weak, and I'll type in weak equals 0, and then display that. And you can see that's isolating just the lower portion of our constraints. So to utilize that weak value, we could drop in a primitive wrangle just before our output, and I'll call this modify constraints. And in here I'll do a check if at weak, then we'll set the float strength attribute to 0.1 so it can break extremely easily. And this is complaining about an implicit cast, so that warning will go away if we just specify weak as an integer attribute there. And if you then check the spreadsheet, you can see that this strength value is being set to 0.1 wherever that weak attribute equals 1. Now you may want to set constraint properties or break constraints or change the constraint type based on some other information in the sim. And if you right click on your object merge for the relationship geometry, you can see there's a whole bunch of data available. Some of this data isn't available until you go a frame or two into the sim, because this needs to be computed by the solver, such as the distance and force and impact. And in this example, we're going to be focusing on the rest length and the distance. The distance is going to be just the distance between the pieces that are constrained together, and the rest length will be that original distance before the sim. Now if you go down to the modify constraints wrangle, we can add a check to compare the two. And in this case, I'm going to check if the float attribute distance is greater than 1.3 times the rest length. So that I'll check if it's 30% longer than its original length. And if so, we'll add it to the broken group with that group attribute shorthand at group underscore broken is equal to 1. Now if you middle mouse on that modify constraints wrangle, you can see that 21,000 of our constraints have been added to that broken group, and we can see exactly which ones those are by dropping in a blast sop. I'll call this check broken, connect the wrangle to that, select the broken group from the drop down, and select delete non-selected. Now this will show us which constraints have been broken based on that rule, and that looks about correct if we compare that to the wrangle that is updating those positions. It certainly looks about right with all of those middle sections and the collision area being broken due to being stretched out. And you can make lots of other changes in these SOP solvers as well, pretty much anything that you can come up with. For example, maybe you want one section to turn into a soft constraint from a glue at a certain point in time. Then you could just change that constraint name attribute from glue to soft. And you can come up with a whole variety of interesting things to do in these constraint SOP solvers. But for this example, I'm going to stick with what we have here so far, and we'll run a flipbook and check our new results. Now if we play back that flipbook, it looks like everything is working correctly, and those soft constraints are being broken based on their stretched out length, and we're getting some pretty cool stuff. The dangling window frame at the top of the frame here is quite nice, and all of this other stuff that's wobbling around It's all pretty interesting, but it does take quite a lot of time to dial in just the right constraint stiffness and the right conditions for breaking those constraints and everything else. So for your shot, you can absolutely just stick with the regular glue constraint setup, but if you have time and would like to experiment with it, I absolutely encourage you to test out some of these soft constraint techniques as well.